Good afternoon and welcome to this session at Big Data London. My name is Dan Chester and I'm joined here this afternoon by Joshua Robinson. Joshua is a founding engineer and lead data scientist at Pure Storage. So Joshua, perhaps you could explain for the audience what Pure Storage is, what they do, and the relevance really for data scientists.
Yes, Pure Storage is a storage company, but really much more than just storing data. We're all about how you can make that data useful for your projects. And this really is important for the big data, AI type of workloads. And the reason we're built what we've built is really to take the advantages of Flash, but build a modern scale-out storage system so that you can really easily store and then use your data. I think that's really the key. We've really always focused on simple. We want to make storage infrastructure that is simple to use. And data scientists, especially data scientists, really take advantage of that because it lets them do their work, which is algorithms, ETL, it's AI, it's machine learning, and not tuning infrastructure, not configuring infrastructure. Okay. And that's really our advantage for data scientists.
And so you're a leading engineer, data scientist at Pure Storage. Prior to that, what was your background?
Actually, as a data scientist myself. My previous job before Pure was at Google, where I worked on the search indexing team. And our job was basically a data pipeline, a machine learning system that tried to understand the internet, which is an impossible task, but actually really interesting. And before that, I've done other startups that tried to use machine learning for various different use cases.
So you've experienced things from both sides, both as a data scientist and in terms of helping to build the infrastructure.
And at my core, I'm a data scientist. I mean, I work for an infrastructure company, but what I'm interested in and what I like to think about is the data science problems.
Okay, so what was your presentation on today? I think you just presented half hour ago?
I did, yes. So the presentation I gave today was really lessons we've learned working with some of our large AI customers. So we have several customers who are much more sophisticated than we are, who have very large AI projects and research teams, and very sophisticated infrastructure. And what we've really learned from them about what makes their project successful. And then packaging those learnings and presenting about some of the lessons we've learned, some of the pitfalls, and suggestions for how to make an AI project more successful or more likely to succeed.
So one of the things that I've heard a lot of people talk about here today is public cloud. A lot of people are talking about public cloud in the context of both general data science and machine learning. When does it make sense to do things in the public cloud versus doing something on premises?
That's a great question, and one that we get a lot. The real advantage of the public cloud is you can get started today. You can spin up, and that's really critical when you're in the first phases of a project, because you don't know yet if it's going to pan out. You don't know if the data set you have has value you can unlock. You don't know maybe the tools that you're going to use. And so at the first stage, you really just need to prove out the idea. And then you can invest more infrastructure, invest more people in the project. So that's really the difference. In the early stages, you want that quick agility, and that's where the public cloud has huge value. But once you're getting to productionizing the system, you have a lot of different constraints. Where you have much more performance requirements, much larger data sets, and continuous operation. You need to keep training, keep updating your AI models in order to keep pace, in order to provide a better customer experience, in order to continue learning whatever it is that is in your environment. And so when you're moving to production systems, normally at the scale that you need to be at, it makes sense to build on-premise and control it yourself.
So we're hearing a lot now as organizations move on from the sort of traditional batch and streaming analytics. They're moving over to machine learning. They're just thinking about that first AI project. I think from the feedback I've had is a lot of people struggle in making that change. What are the key differences between traditional analytics and machine learning, and what are the key things that people can do to be successful?
So that's a really great question. The key differences between what I would say is older big data projects, which are Hadoop-based data lakes, and where the world is at today is really infrastructure agility. And so what I mean by that is you have to be aware that multiple different applications, multiple different use cases are needed to really have a successful AI project. It's not just one application. You have many different phases of bringing the data in, processing the data, and then learning from the data. And that produces a lot of different demands on the infrastructure. And it also means that keeping up with the open source community and the pace of adoption and evolution of new technologies is a challenge for a lot of that old infrastructure models. And so generally I think people tend to think about it as how much data can I store? But in reality, what I tell most people to think about is how can I enable my developers, my data scientists to be agile, to do multiple experiments per day instead of one per week. And I think that's really the key because at the end of the day, most of the customers are thinking about 6 months, 12 months, 18 months, getting this AI project to completion. Maybe it's a product, and if they can cut it from 18 months to 6 months, that's a huge benefit for them versus their competition, because it's a first to market in a lot of these circumstances.
So what would you recommend that they did in order to achieve that?
Absolutely, so the key there is disaggregating your compute and storage.
Okay.
So what that really means is going away from the model of direct attached storage, which is what really Hadoop made famous. And so that's a single node that's both compute and storage. But that adds a lot of rigidity and prevents you from doing that quick adoption. But disaggregation is you have separate compute storage resources that you manage independently. Now, the compute side, you can use virtual machines and containers that make it really easy for you to do experiments and to scale up and down your applications. While at the same time, you can scale up and down your storage requirements separately.
Right.
And that gives you ability to decouple. And when you do that, you get to move a lot faster.
So obviously a lot of organizations here at this event will have been working with Hadoop. How would you recommend that they move from that sort of traditional state of data lake into a more modern world?
That's a really good question, and frankly a little bit of a hard one. Normally what you need to do is identify those data sets that are really valuable and what you want to be able to take from where they are now into something that you can say is a business outcome. Now to do that, I think you're moving from a batch-oriented architecture system, and so most often what happens is a customer is moving from that batch system to a streaming system.
So maybe moving from Hadoop to Spark?
Moving from Hadoop to Spark, exactly. And it comes with it a new set of infrastructure. So an infrastructure that can handle the demands of running both streaming and batch workloads at the same time on it. And so I think that's the natural point in most cases to switch over to new infrastructure is your batch system is in one place, and then the demands of a streaming system require a new set of infrastructure. And then finally, the other point is, once you want to start introducing heterogeneous hardware, for example, GPUs, that's a really good time to make a change in the architecture because those heterogeneous hardwares introduce entirely new demands. Basically, you have a supercomputer in a box, which is a very different type of workload, different type of applications than traditional big data applications were 10 years ago.
And in terms of the underlying storage medium, so traditionally Hadoop was based on disk-based storage systems, obviously Pure's all about Flash. What does Flash bring to the table in terms of these types of workloads?
That's a great question. So Flash specifically brings a lot of performance, but it doesn't bring it just because you have Flash. What we needed to do at Pure was start from scratch and design an entirely new storage system that was from day one built for Flash. And Flash is a strange physical medium. It's very much different than hard drives. And so it really takes a different design. And what's turned out to be the case is database techniques work really well with the way Flash works as a medium. So what we've actually built is a distributed key value store, not a file system or an object store. So we built that distributed key value store and then built the tables on top of that to make a file system. But by creating a system that is fundamentally a database, it means that we can do all of our lookups and all different types of operations efficiently. So instead of being just optimized for sequential streaming workloads, we can do a mix of workloads. So small files, metadata, and large files. And that's really because we unlock the full performance of Flash by having a purpose-built system for Flash.
And I think one of the things that you've talked about is the different types of workloads within that data pipeline and how that has different demands on the underlying storage.
Absolutely. If you look at the ingest or ETL phases of a pipeline, they have different demands from when you're training an AI system, which is a really intense computationally workload. And further, when you train an AI model, what you're actually doing is taking your entire data set, reading through it multiple times, but shuffling the order every time.
To avoid overtraining.
Right, so that shuffle actually gives you more robust models, a more robust AI, but it is basically the worst case scenario for a caching workload. So what you need is a storage tier that lets you have your full data set available at any given time so you can keep the GPUs busy while you're training.
Okay. So taking off your pure storage hat for a moment and wearing your data science hat, what do you see as the key trend or trends over the next 5 years in data science?
Absolutely. I take off that hat frequently. I think the key trend really is bringing tools from the frameworks and from more packaged environments so that you can really democratize data science. You don't have to have a PhD in order to take a data set, make something useful out of it, and turn it into a product or an internal process automation, whatever you need to do. And it's really removing the requirement for a PhD level of expertise, whether it's from managing the infrastructure, and that's really where, again, Pure comes into play, but it's also in just making sense of your data, using the algorithms, and we're starting to get much better at creating tools that are more accessible to most organizations.
And any particular favorite tools or techniques that you've seen emerging recently that you think are ones to watch?
I would hesitate to bet on that. I'm not sure who will end up winning, but I think you see, what I see now is, and what makes me really happy is to see tools like Spark come out as built from the beginning as a scale out tool. And it really natively works in that manner, because at the end of the day, what you don't want to do is have a system that's running for 9 months, but then because you've grown, need to redesign it completely. That slows you down and that stops you. And so what I've always been looking for is tools that help scale out. An example from the AI world is something like Horovod, which helps you scale out your deep learning training across multiple GPUs. And with that, you can much easier go from small proof of concept to full-scale production without having to redesign and re-implement the systems. And so I'm always looking for tools that natively scale out.
Great. So again, many of the people here at this event will have been doing that early stage exploration. They'll probably be using the cloud because it's easier for them to get some resources provisioned. For those people that are early on that journey who are listening into us today, what key thing would you ask them to take away? At what point in their journey would you suggest they come back and rethink again about that on-premises versus cloud trade-off?
Well, I think the key thing that I suggest is to really focus on the data. I know that the algorithms, the neural networks, they are the coolest
stuff. Yeah,
that's the coolest. But the data is actually underpins all of your success.
Yeah.
And so I've seen a lot of customers who have had successful projects with, frankly, very unsophisticated algorithms because they have the data set.
Right.
And so I think the real tip over point is when it's time to invest in a large data set. Obviously, some use cases have much smaller data sets, and they can fit in the DRAM of a GPU, for example. But when you need that larger data set and take the full value of that, whether you're using a sophisticated algorithm or a simple algorithm, that data set size is really the tip.
So size is a key one. Thank you.
Size.
Thanks very much, Joshua.
Thank you.
Thank you.